Hey guys, so I'm gonna make this video as quickly as I possibly can. I know I always say that it's gonna be a quick one, a short one, but this next subject, stereochemistry, is probably, or I promise you almost, the most in-depth. It's not the hardest to understand. It's really not. It includes a lot. And there's a lot of different concepts or natures of things you have to understand if you can't already picture them in your three-dimensional head. But everyone can, so don't worry. So we're going to start from the basic. I'm going to keep it as quick as I can. You guys have a worksheet due. First off, I want to say, do not freak out if you're getting the wrong answers or you're not sure about your answer on your worksheet. Up until now, I'm certain that you've all felt quite certain about your answers on your worksheets as you submit them. However, for this upcoming one in Stereochem, I expect most of you, even the top students who always get hundreds, and actually nobody gets hundreds, but even the top students who get highest grades, they're going to start to question themselves and think, all right, well, did I get this right? Did I not? All right, I should probably send Matt a million emails. Send me any questions you have, but please don't send me like more than 5 emails in a row. I do get that sometimes, and I love hearing from you guys. It's like I live for that. I love answering your questions, but it's this is going to be a very tough subject, and my review video that I'm posting here on YouTube will be the least of your help. And since it's the very beginning of the video, I'll give this disclaimer. If you watch Dr. Shia's videos on stereochemistry and all the other subjects up to this first or second exam, you will do extraordinarily well. I promise you that. That is a promise from me to you. Dr. Shia is a remarkable teacher. Her reverse classroom style, aka you go home, watch her lectures on YouTube whenever you have the free time, and you show up to class. And she perceives you already understand the material, so she just puts like a mini quiz up on the projector. And she asks the class questions, and they put it in on their turn it in tags. Typically, if it was a regular semester, we were in class or in lab, that's how it would work. And she prefers the reverse classroom. I learned directly from Dr. Shia initially when I began organic chemistry. I ended up switching my major from pre-med to chemistry, and then finishing my bachelor's 4-year program in chemistry at the top of my class. And it was all because of Dr. Shia. And it started with her organic reverse classroom YouTube videos. Do not take them for granted. I highly recommend them. I fell in love with chemistry in high school, but I am the chemist I am today because of that woman and because of those videos. She is an absolutely remarkable scientist, and I highly recommend all of those links, which will be at the bottom of this description, as well as the review for Stereochem that I reposted. That was Zach's video from the lab. Anyways, let's dive into stereochemistry, guys. So first of all, E and Z configuration. Whoops, I just realized I haven't shared my screen with you guys yet. So let me do that real quick. Share screen. Just share. All right, cool. So let's start off with E and Z. So first off, E and Z. This, I believe, is the most basic, and I've ordered all of these ridiculous tabs with specific images. I've taken off Google Images or Bing Images, whichever, that I have deemed credible enough for your education and for my literacy or literate descriptions. Anyhow, E and Z just refers to double bonds, and so with a double bond, you can have this kind of configuration, if you follow my mouse, called trans, or you have this kind of configuration called cis. And we call it trans because each side of the double bond, the main group is in the opposite direction. And on this side, it's cis because they're in the same direction. Now, the thing about a sigma bond versus a pi bond is a sigma bond is this single bond going from here to the R, right? Now a pi bond is this floating line right here, correct? Now whenever we see a sigma with a pi, we know it's a double bond. Whenever we see a double bond, I want you guys to think of, and I'm trying to describe this in a way, I know most of you have your model kits, but I'm also trying to describe this in a way for those who do not. Because I know a lot of you are in foreign countries, and unfortunately right now trade is down, and you have no access to model kits, and there are no model kits apparently online in your country for a reasonable price. It makes sense depending on where you are. However, I want you guys to picture it like this. Right now I have a hairbrush in my hand. We're going to pretend this is a sigma bond, a singular bond. All right. So we can rotate it, and if we're imagining that it's a straight cylinder, totally symmetrical, it does not change. Now let's pretend that this remote right here is also a straight cylinder, totally symmetrical. Now you cannot rotate both of them in the same plane without changing their symmetry, but you can rotate the singular cylinder without changing its symmetry. But you can't rotate these without changing, because right here it looks like a line, but right here it looks like two lines, right? So they're locked. So in that circumstance, a sigma bond, a singular line, can rotate in either direction. All right, we're going to pretend it has a pivot on it. Now each of those lines has a pivot. Just because each of these bonds has a pivot, since they're linked together, they can't pivot individually, discretely from one another. So they're locked. That's how we get the E and the Z conformation, because if something is pointing in this spatial direction and something's pointing in that, if there's a double bond between them, they're locked in that spatial configuration. So we end up with E. And the E actually stands, a lot of this chemistry, actually all of chemistry and all of science in general came directly from Europe. So a lot of the translations you'll see will be German or French, etc. German for most chemistry and French for a lot of biology, I've noticed. Physics is the most foundational science, just put it out there. And mathematics is the universal language which unites all of them. But E and Z configuration, and the E stands for entgegen, which is opposite, and the Z stands for zusammen, which is same. And those are both German terms, and that's why we have trans cis. So moving on, you have R and S configuration. So here I found a picture where we can see we have some sort of molecule, and I hope you've seen something similar to this, where you have a bold, and we're going to pretend the vertical, even though it's not shown here, we're going to pretend the vertical line is a bold wedge, so something that buds out like this in dark bold, and that feeds to the 1 and 2 and the 1 and 3 on either the left and right side or in plane. So with the way you determine R and S configuration is you look at how 4 different atoms are arranged. And here are 2 different examples where you have on the left side 1 tetrahedral configuration, on the right side another tetrahedral configuration, where they're in the 2 same molecules. They both contain 1s, they both contain 2s, they both contain 3s, and they both contain 4s, but they are in different spatial configurations. So when you observe them, you notice the left side is an R configuration because we can count 1, 2, 3. And now you assign priority to those certain groups based on their atomic number, okay? So we know atomic number is the number of protons of the element, all right, on that atom. And we can determine that by the periodic table, but mostly those elements will always be carbon, which is hydrogen, which is 6, oxygen, which we know is 8, I believe. Carbon, I believe, is 6 or 12. I believe I'm mixing up its atomic number with mass, probably, which is why I hesitated earlier. Apologize for that. But you always number from highest priority to lowest priority from the count of 3. Now, the thing is, the only exception is when your lowest priority group is coming at you. And that's the wedged dark line. And now that's when you switch configuration. Now, if I have an example, and I wish I had one up on the board for you. Actually, maybe I can scoot ahead and find an example. Sorry about this, guys. Okay, no, so I'm just gonna go with this. Anyhow, so an R configuration you can count on as being clockwise, and an S configuration count on being counterclockwise. So you look at the atoms surrounding the central atom here in a tetrahedral configuration, you look at their atomic numbers, and you should have them memorized. I'm not saying memorize every single atomic number of the elemental periodic table. I'm just saying the most common ones, which are carbon, hydrogen, oxygen, and nitrogen. So you assign them based on their atomic number, their priority, okay? And now hydrogen, proton, is going to be the lowest priority because as we know, or as I hope you know, with chiral atoms, that means that all four substituents, meaning all four atoms coming off of the central atom, are completely different, meaning they're not the same element. And that being said, if your lowest priority element or lowest priority substituent coming off of the central atom is coming at you, you count the priority of the other elements or atoms surrounding the central atom, and then you look at the counter or regular clockwise configuration, and if it's R, you reverse it to S. If it's S, you reverse it to R. And now I believe I just confused the crap out of you, so I'm going to try and elicit. In this example, if the 4 were the proton and all these other 3 were completely different elements, like we have an OH here, a CH3, and a CH2 right here, and this is the proton, the H, this is a chiral atom, and you can count on this as being clockwise. Now the same one right here, I'm not even going to the right side, I'm still looking at the one that's labeled as R configuration. Pretend this is a CH3. Now this is your CH2, this is your OH, and we're going to pretend this is coming at us. This is the wedge, the black wedge that's coming at us. This is going to be a proton. Now we'll reverse it when we label it, even though we count it as bang, bang, bang clockwise, we're going to reverse it and call it S configuration because the lowest priority group, the hydrogen, aka the proton, with the lowest atomic number is coming at us. And I really hope my screen was shared for that. If it was not, I will just quickly reiterate. I'm sorry, guys. That's all right. So isomers, moving on. Stereoisomers. In order to determine how many stereoisomers that a compound has, you want to determine how many chiral atoms there are in the molecule, and then take 2 raised to that number. So we call it 2 raised to n, where n equals the number of chiral atoms. And now a chiral atom is an atom in which the 4 atoms that are bonded to it, if it's a carbon, then it has 4 bonds, remember, they're all different. So you have an OH, a CH3, a CH2, and an H, for example. That would make a chiral compound. For example, if you look where my mouse is, this carbon right here, this is a chiral carbon because it has a Cl, a Br, an F, and an H, and those are all completely different. Now, when we're talking about stereoisomers, you can determine how many stereoisomers because by looking at the singular compound, we can say, all right, there's 1 chiral compound. So 2 raised to the 1, 2 to the 1 power is 2. So we know there are 2 possible stereoisomers. So for this compound, the singular carbon bonded to chlorine, fluorine, and bromine, there are 2 possible stereoisomers based on the 2 raised to the n power to find out how many possible stereoisomers. That will probably come up on your exam. So make sure you remember the 2 raised to the n maximum rule. And that's the maximum number of stereoisomers. And I'm going to address this more in a few moments. But if you have meso compounds, that 2 raised to the n power will be decreased by 1 because meso compounds, they're 2 they're two compounds that seem like they're like just two different compounds, but they're actually one and the same. I'll address that in a moment. But anyways, moving on again. So from isomers, we move to constitutional isomers. And here we have an example if you follow my mouse. If you observe the chemical formula of both of these two compounds, you see a C3F1H7. And same thing here, C3F1H7. The only difference is an F and an H have been switched. That's how you call it constitutional. That's pretty simple to understand. I hope you all get that. Moving on, we have the difference between enantiomers and diastereomers, and I'm going to go into this in further depth in a moment. However, the difference between enantiomers is that these are two compounds with the same chemical formula, however different, and stereoisomers are different, are spatial isomers, meaning instead of just having the same chemical formula, they have the same chemical formula, but they have a different spatial format. So for enantiomers, you have mirror images. So they're mirror images, but they're non-superimposable. And superimposable is a term that means, so I have a left hand and I have a right hand, right? And they're mirror images. If I put them right like this in front of your camera, it looks like it's mirrored. But I cannot get one to perfectly overlap the other. Because say I try and overlap this hand with this, these fingers are going to overlap, but it's going to be my pinky on my right hand with my index finger on my left, and then my thumbs don't even line up. They're non-superimposable. I cannot perfectly fit one over perfectly into the other, so they're not identical. If for example, this, if I had two identical towels, for example, identical, perfectly the same, and they were folded the exact same way, and they could fit and overlay into each other, they would be an example of something that was superimposable. Now, enantiomers are non-superimposable, diastereomers are non-superimposable. So what I just taught you about being superimposable, being able to overlay something, meaning it's the same, the identical thing, they're both non. Enantiomers are mirror images, diastereomers are not mirror images. That's where they differ. So they are both non-superimposable, but only enantiomers are mirror images. Diastereomers are non-mirror images. Now, enantiomers can have the same physical properties, but diastereomers can have drastically different chemical and physical properties. For example, thalidomide. You can have the left-handed and the right-handed version of thalidomide. In the 60s, it was used as an anticonvulsant drug for pregnant women with morning sickness to prevent it. And it got passed in Europe. So all over Germany, and a lot of France, and the Czech Republic and Sweden, etc., they used this drug, approved it by their version of the FDA, and years later, all the children that were born in that time frame, whose mothers took that drug, were with horrible birth defects. And there was one woman from the United States actually who campaigned against this and stopped it from happening in the United States in 1960 to 1964. And that's actually the reason my uncle doesn't have these wild birth defects, because my grandmother on his side took thalidomide to help with, at the time, because it was a popular drug, to help with morning sickness when she was pregnant. And if she had been on the European approved version, then my uncle actually would have been born with horrible birth defects, and he probably wouldn't be alive today. He's 63 today. But anyhow, moving on. Cis-trans isomers, we talked about that. The E versus Z, the anti-again versus Zusemen. Then we have conformers versus rotomers. Now, conformers are different molecules that they have the same chemical formula, but they differ by multiple rotations or configurations. Now, rotomers only differ by a singular bond rotation. And now this is what my next slide is about. I'm going to dash these next because I know I've used up a lot of time on the past 2 slides. But Conformers versus Rotomers, this is just a quick Bing search, guys. So it's out there. The information is right there. You can't trust a lot of Wikipedia, but I proofread this first little paragraph. So Conformers and Rotomers is that conformer is chemistry, any set of stereoisomers characterized by a conformation that corresponds to a distinct potential energy minimum, while rotomer in chemistry, any set of conformers that arise from restricted rotational around a single bond. So a singular bond rotation is a rotomer. A conformer is the same structural constitution, the same chemical formula, but multiple bond rotations. So it can be diastereomers, which there can be many of. Enantiomers have mirror images, but diastereomers, there can be many of. And I do apologize for the length again of these videos. I really do not support the fact that my videos keep getting longer. I'm trying to make them shorter. Sorry. Anyhow, conformational isomers, moving on. So here, the difference between a conformational and a constitutional. So we talked about conformers versus rotomers. So conformers and rotomers are both conformational isomers. They differ by 1 rotational symmetry difference versus multiple. Here we're looking at the more blatant conformational isomer. You will not be tested on conformers versus rotomers. If you are, I will be very disappointed in your lab instructor. I know Shia will not do it, so I will be very disappointed. But I very, very, very do not expect that. However, the conformational isomers you will be tested on is a difference of a singular rotation, at least at your level it is, and I expect in your exams and in your worksheet I know it is. So here, for example, you have a Newman projection up top. Here you have an eclipsed example, and I'm going to go into that more detail later. Here you have a 60-degree rotation, which brings you to a staggered example, aka a gauche. So that's when it's not quite anti, but you can see there's 2 CH3 groups are the highest priority because all we have is protons around here, if you follow my mouse. So they're gauche, we call them, when they're directly next to each other, separated by 60-degree rotation. And then here we have the ball and stick formation. And you have the 2 aligned here, so that's eclipse. That's the same thing, the top and bottom right here, the Newman versus the ball and stick, the same thing. So we can't literally draw a line over a line with the Newman projection. That's why it's at a slight angle, but it's literally overlaying one another. We just can't interpret that on a 2-dimensional surface. That's why we have the Newman projection at that like slight angle, even though it actually represents this. And then here we have the gauche, and that's what it looks like in the ball and stick, where they're just separated by 60 degrees across this one plane. Moving forward, we have the constitutional isomers, and now here's a great example of constitutional, and I can not zoom in currently, which I was hoping I might be able to, but that's all right, because here you can notice that they both have the same chemical formula, but they have different orientations. So the Cl is on this external carbon here, this primary carbon here, as opposed to the chlorine being on the secondary carbon located in the middle. So these 2 compounds are different because they have different stabilities, solubilities, etc. However, they have the same chemical formula. So they are constitutional isomers because you just switch 2 atoms. Now enantiomers versus diastereomers. Now I'm going to get in a little more detail. Enantiomers are stereoisomers that are non-superimposable, but they are mirror images. So they are mirror images of one another. If you put one next to the other, you'll notice they are symmetrical. Diastereomers are stereoisomers that are non-superimposable, like my hands. All right, they're mirror images, but they are non-superimposable. They're just like diastereomers. Goodness, sorry about that. They are mirror images that are non-superimposable. They're just like enantiomers. Mirror images that are superimposable are the same molecule. Mirror images that are non-superimposable are enantiomers. Mirror images are non-mirror images that are non-superimposable are diastereomers. So there can be several different diastereomers. There are always enantiomers in pairs. So because I said a mirror image, if there's one enantiomer, there's always another. It's its mirror self. So the thing about this thing, this one fact, is a little untrue. Diastereomers and enantiomers can have wildly different physical and chemical properties, as we see with thalidomide, where one is an anti-convulsant morning sickness pregnancy drug and the other causes horrible birth defects. But one thing you can believe here is that enantiomers rotate plane polarized light in opposite directions. So essentially that's light, a photon emits light, or aka electromagnetic radiation. So 90-degree perpendicular electricity versus magnetism fields, which creates light, which creates photons. Those fields rotate and they go out in every single spatial direction. However, when we use a Nichols prism, and that was something developed by William Nichols in 1828, it's a specific type of calcite crystal which takes in a very specific wavelength of light, eliminates all of the ordinary light, and only allows this extraordinary light to pass through. So we can measure difference in polarization, and that's the curvature of the light. So light emits in every direction, all right? So not just X and Y, but in Z, so coming at you and away from you. So literally every direction. However, when we use a Nichols crystal, it separates all of that into singular plane. And now, in order to differentiate between different enantiomers, we run them through a polarimeter. And a polarimeter has a Nichols crystal that focuses light in a singular plane. And these certain chemicals rotate that light in either a positive or a negative direction. The positive is the clockwise, and the negative is the counterclockwise. And the angle of separation from the polarized angle of the light to where it's now been adjusted to by your compound is called the alpha angle. And now for more polarized compounds, you have a larger angle, and for less polarized compounds, you have a lesser angle. And now for compounds with higher concentration, because you have more of that compound, obviously you're going to get a higher alpha, and with a lesser concentration, it's going to be lower. So we can assume that, and it also has to do with the path length. So say you have a tube, this is just an example because you wouldn't actually use PVC, but say you have a PVC pipe tube, and it's this long, and you're passing your plane polarized light through it, through a Nichols prism over here. Now, the length of the tube has to do with how much it rotates as well, because your light is only going to rotate at a specific acceleration, correct? So if it has a longer amount of distance to travel, it's going to rotate more, right? So it depends on the path length of a tube, it depends on the concentration of your solution, and it depends on the substitution of your compound itself, like what it is, to be honest. But that's how we determine. So we know that alpha, the specific rotation we call it, and I'll talk about that a little bit more in a bit, is the curvature of the light, the singular polarized, plane polarized light, what angle it curved by, passing through your chemical of question. So moving on, as soon as this menu pops back up. Sorry about this, guys. All right, so here's a Nichols prism, polarizing prism to kind of display. So here, if you follow my mouse, we have unpolarized white light. It goes into the Nichols prism. The Nichols prism pushes off ordinary light, anything we would expect, and we can develop the calcite crystal based on any wavelength of polarized light that we would expect. So anything that we would expect, we would enter into this algorithm. It would counter for it, and anything extraordinary, we would be able to see. And that's how you record it with the Nichols prism. Moving on, Meso compounds. This is pretty important. So they're achiral, meaning that these are compounds that, despite having chiral centers, the opposite of this chiral center is symmetrical. So the thing is, a mirror image is superimposable. So they end up being the same molecule. That's why with the developing stereoisomers, the 2 raised to the n, with the n at being the number of chiral carbons, it changes for meso compounds. Because if there's a singular meso compound, that means you subtract 1 from that 2 raised to the n. Because a meso compound is identical to its mirror image. And its mirror image is also superimposable. That's what it means to be identical, is to be superimposable. So you subtract 1 because they're the same image. So even though you got 2 raised to the n, you might get 16 for, like, for example, D-glucose if you watch Dr. Shia's videos. If there was a meso compound in question there, then you would subtract that and you would actually be 15, even though for the max equation you got 16 as a result. So moving on, racemic versus meso compounds. Now, a lot of people mix up these two terms because they like to think like, oh, racemic, meso, they're the same thing. Not really though. Just because you can put a line of symmetry there doesn't mean that it's racemic or meso. The thing between racemic and meso is that meso compounds contain identical mirror images, and racemic contain non-identical mirror images. So the thing about it, racemic mixture is a mixture of 2 enantiomers that polarize or rotate polarized plane light in opposite directions by the same capacity. So if you took a racemic mixture, so 2 different enantiomers, mirror images, and they rotate plane polarized light by that alpha degree. This is like 45 degrees, and this is a negative 45 degrees. It's going to cancel out. Racemic mixture, enantiomers, cancel out. So you're going to see 0. And then a meso compound, they're the same. So you're going to see 0 result. So in a polarimeter, you would be like, all right, there's no difference in either of these. However, in a racemic mixture, you would see no difference from the original alpha angle. And the meso compound, you would only see from the 1, you would see no difference from the 2 mixtures. Because as we know from meso, the 2 difference between meso compounds is that you can superimpose them, meaning they're the same. Not my hands, they're not the same. You can superimpose meso compounds. Racemic mixtures, they're mirror images, just like my hands. And they rotate plane polarized light to the same degree in opposite directions. So this one is rotating plane polarized light in this direction, and this one is rotating plane polarized light in this direction, and they cancel each other out. And so you see a similar result to the meso compound in the polarimeter. Moving forward, we have Fisher projections. Just to describe this, it's pretty simple. Here is how you'll see it on your worksheet or on your exam. I want you to know all the vertical lines are coming at you. So there are these wedges that I described earlier. And now the horizontal lines on either end are going away from you. And notice how there's a dotted line here in the middle, and now you're going to have questions about that. I want to say, picture it like a centipede that's like curling it. Right. So we're going to pretend my arm here is a centipede, or this molecule. It's curling in on itself. And at every joint, my knuckles right here, at this joint, my elbow, down to my shoulder, there are things budding out, and they're budding out like spikes coming out like a stegosaurus's back, right? So a stegosaurus has 2 spikes per like point, correct? So you have 2 different points coming out in opposite directions here. That's how a Fisher projection is. And your sight, your line of sight from the tip of my finger here, that's your eyeball. You're looking in this direction. So you're pretty much looking at something that's been wrapped over, crawling towards away from you. So crawling in the opposite direction. Here's your line of sight. You're looking down at it. Here's your dotted line. Here's your dotted line. Here's your compound going in the opposite direction on the top. And here's your compound going in the opposite direction on the bottom. And here, imagine 2 substituents coming out at you. Here, imagine 2 substituents coming out at you in that direction and that direction. Here, the same thing, that coming towards you and going away from you, but in that direction. That's exactly how a Fisher projection works. It wraps around, and anything on a vertical line is dotted in the middle and coming at you, or going away from you, sorry, at the ends, and anything on a horizontal line is coming towards you, because it's wrapped around like this. And if you do have a model kit and you arrange a straight carbon chain like this, and you just try and circle it around, eventually it'll meet in a circle. But if you just look at, I don't know, 4 carbons or 5 carbons in a row, the spines are going to come out all around the back like this. That's how you should imagine a Fisher projection, because that's how it's projected. Now, a lot of chemists don't like this projection because that's not how molecules arrange themselves in ground state and at the most stable state in nature, but it's one way to elaborate on them. Now, here's an example where you can see the difference between a sawhorse projection, a staggered and eclipsed, and a Newman and a Fisher projection. We're going to focus on the Fisher. So here's the Fisher we saw, and here's the same exact Fisher. Now, it's not quite the same, because what did I just say? What do we know about it? If we took this one sigma bond here, if you follow my mouse in the sawhorse projection, and rotate it 180 degrees so that the CH3 and this CH3 were facing the same direction, that would be the exact equivalent of this right here, Fisher projection. And it would also be the exact equivalent of the eclipsed projection of the Newman projection right here. Now we're about to touch on Newman projections. Newman projections are these strange circles you guys are seeing, and the Fisher projections are these up vertical and horizontal lines. The sawhorse, or the ball and stick, or the ball and twig, are these projections here. Now we just spoke about Fisher. Now if you picture a molecule, and if you have a molecule kit, you'll know that this is wrapped around. So this Fisher projection is showing this exact molecule in the same spatial configuration as the eclipsed Newman projection. But this sawhorse projection is showing it in the same spatial projection as the staggered Newman projection. Because we know in a Newman projection, the circle in the outer rim represents one carbon, and the dot, the vertice in the center where the three lines interconnect inside the circle, is another carbon. So we have a dot here that represents one carbon, and a circle on the whole outer rim, if you follow my mouse, that represents the second carbon. So you have a methyl, 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 methyl. Same thing as the sawhorse projection, and they're on opposite sides. Now here we have an eclipsed, where we have rotated it completely around, and now we have the same thing as the Fisher projection, which is always represented as the top and bottom going away from you, and all vertical lines are going towards you. So moving forward, here's another example of the staggered versus the, or the anti versus the gouge, both staggered examples. So here you have the sawhorse projection of either of them. So here you have gouge CH3 to CH3, because you have one coming at you and one within the plane. And then here, if you notice, they're both just regular lines, so they're in the same plane. So they're opposite one another, correct? Yes, you know this, because this one's coming at you and this one's going away from you. So this proton here is in the same plane as this proton here, which means that this CH3 is in the same plane as this CH3. So if these two are gouged because they're right next to each other, this one's coming at you and this one's in the plane directly 60 degrees rotated into plane away from you, then we know these two on the regular lines are anti from one another within the same plane. So moving forward, as soon as, sorry guys, the menu pops back up, and I know I'm taking a ridiculous amount of time, and I apologize. So here's an example where we see the Newman projection, the sawhorse projection, and we get a nice example of the RNS. So here we have the green lining up with the green and the purple lining up with the purple. So this outer circle represents this carbon here, and this inner dot represents this carbon here. And that's how you change Newman projection to the other, because these are the same exact compounds, guys. This CH3 is coming out at us, this one as well. This proton is going away from us, this one as well. This bromine is in plane, this one as well. And the same exact thing on the opposite side. They're the same exact compound. So that's how you transmute a sawhorse projection from a Newman to a Newman projection. Moving on. All right, so Hayworth projections. You guys won't have to focus on this as much, but I want to focus mostly on how you transmute a Fisher projection into a Hayworth. Now, a Fisher projection shown here, the glucose, a 6-carbon Fisher projection with 4 chiral carbons. The way to turn this into a Hayworth projection is just to, so if my vertical hand here is exactly how you see it on the screen, the D-glucose Fisher projection where my mouse is, turn it on its side like this. So the CH2OH is on your right where my mouse is, and the aldehyde, the CHO, is on the left. Now curl it around, and that's exactly how you get your Hayworth projection. And you can count the carbons and figure it out right here. It just curves around. And if you lay the Fisher projection on its side and curl it up and around, that's exactly how you can determine your Hayworth projection. projections. Just know that these are coming out at you and these are going away from you. The carbons within the hexagon. So they're bolder line because they're closer to you. That's what the impression is supposed to give. Now, moving forward, we know that these wedges here come at us and these dashes here go away from us. So when you're observing a molecule like this and you need to go to chair conformations, now addressing chair conformations, we've seen them drawn like this. Practice drawing these because they're a pain in the butt to draw. Pretty complicated, to be honest. Because I messed them up for years, just like throwing them in. And I did so well in my exams, they looked so bad. Like little weird rectangles, so practice. But anyhow, you can see here that the chlorine and the chlorine, that's going away from this, that's coming at us. They're opposite. And here, in the same exact molecule, but drawn in the chair conformation, they're also opposite, up and down. And now here, you have the CH3, the methyl group, that's at the 1 carbon. It's going the same direction as the chlorine at the 4 carbon. Now here's the chlorine at the 4 carbon, they're both going up. Notice that. But this is in red. That's because it's an equatorial. Now the difference between equatorial and axial is that equatorial is anything except a perfectly vertical line. Axial is a perfectly vertical line. So here you have axial chlorines. Here you have an equatorial methyl. Equatorial is the more stable of the groups. And that's because it's within the same plane as the majority of these other carbons. If you can picture it in the 3-dimensional plane and such, and I have an example of that right here. Here's an example if you have a model kit, what it would look like to have a chair conformation and to look from it from the right angle, the correct angle, I should say, correct angle. Just like this image that we're so used to, it looks exactly like it. You just have to look at it from the correct angle. That's all. And it has 3 little bottoms, and there are 3 little bottom pegs that stick directly anti-vertical, holding it up. But anyhow, moving back. Alrighty, so there are 2 different chair conformations. There's the chair conformation, there's the boat conformation. Now, when you're using chair conformations, most of the time you'll use the chair. The only time you'll be tested on the boat, usually in your entire career, will be in organic chemistry. And here's the difference between the chair and the boat. And if you have an actual model kit, you'll be able to see that with the chair conformation, you have 3 downwards axial. So like I just said, it'll be standing on 3 legs. Whereas the boat, it has 4 at an angle. So you'll have 4 legs, but they'll be slightly staggered out like this. It'll be more like a wrapped up table. And this is exactly how a hexagonal molecule will look with your model kits in a boat conformation versus a hexagonal model kit or a hexagonal molecule with your model kits in the chair conformation. So when you flip, notice that you don't have exact axial anymore within the boat conformation. You have a bunch of more random angles, which is why the chair conformation is usually the more preferred. It's the more stable, just because you end up with a lot more perfectly equatorial angles or perfectly equatorial bonds, which are more stable, as opposed to the boat, which is just random everywhere. I know the axial are supposedly less stable, but by balancing them away from the central atoms, by balancing the equatorial in opposite directions, in the further X plane as opposed to the further Y plane, you're able to stabilize chair conformation as opposed to boat. It's important to know boat just for your exam. Other than that, you'll only see it in rare cases in research. But it's very, very important to know because you could overlook something very important in research if you don't know that. Here's another example real quick of the chair conformation, which you will see when it gets flipped. So here we have 1 chair conformation. Now, when they ask you to flip a chair conformation, you can do this with the model kit, and you just turn it like this. So all the bonds are still connected in a hexagon. However, when you turn one end about 60 degrees, their connection rotates on 2 different bonds, and it changes the conformation of the hexagon. So it stops looking from this point on the left to the point on the right, going up and down. It's point on the left and the point on the right going down and up, the opposite, vice versa. And as you can see, when you do that, this 1 methyl is the same methyl here. They're the same compound, they just got flipped. Now, you have an axial here. When you flip it, you get equatorial. Now with a chair conformation, you're going to get an equilibrium between the axial and the equatorial, the chair flips. And you know, equatorial is the more stable. So the larger priority groups are going to favor the equatorial. So you're going to have a larger equilibrium favoring the side that favors the equatorial position of your larger groups. And that's why it's important back here to know which groups are going away and which groups are coming at you. Because if you have a larger priority group coming at you, you want to make sure you put it, or let's use it as the method. If you have a larger priority group, let's pretend this is a large priority group coming at you, you want to throw it in the equatorial, because you want the large priority groups like a COOH, or carboxylic acid, to be in the most stable configuration. You want it to be in equatorial configuration. So moving forward here again, I want to address this again. Here's an example of your model kits. So if you have the model kit that was recommended for this class, if you don't, it's okay. If you do, this is what it should look like in your chair conformation, and this is how it should be perceived when you look at it from the angle of the chair conformation. You have your axials in purple and your equatorials in black. And now if you look at this in a three-dimensional perspective, if you actually had the model kits and you built this, you would notice that it's a hexagon. It looks like a little table and a weird structure. And that's why it's drawn like this, because it's literally represented exactly like that in the three-dimensional plane. But when we draw it on paper, it looks like this. Now, the last thing, again, when you flip chair conformations, here's your CH3, and this is a flip chair. Everyone goes from equatorial to axial. We know equatorial is more stable, okay? So for this example, you have the chlorines, they're anti. They're going opposite one another on these bonds. Now here they're also anti, because even though they're still equatorial, one chlorine is going in the upwards direction, one's going down. So they're still anti, but they're equatorial, so they're more stable. Now in this example, the chlorines have the higher priority, being the higher atomic number atom, and the methyl group is just pretty low in polarity, reactivity, and atomic number in general. So you would actually prefer this right side molecule in this exact example to be the more stable configuration and the more appropriate configuration, because the equatorial chlorines would be more stable and they're higher priority groups, and you have two of them as opposed to the one methyl. I know that this wasn't enough to answer all of your questions, even though it took up a much larger amount of time than I had perceived and hoped. But if you are inconfident on the worksheet, please do your best. Do not worry. Submit, because you are all in my labs. I can't speak for every section, but I know that my 2 out of 8 to 10 sections, or maybe 16 actually this semester, are doing extraordinarily well. I would not worry about your grades or how they're affecting your orgo exam grades. Also, I decide the final exam grades, and I've been in pretty decently detailed close contact with most of you since the semester began over email. So I kind of rationalize and determine how much help you should get, and I pretty much give everyone as much as they deserve. It's almost unanimously 25%, which is exactly the maximum that you're allowed for a lab. I'm not harsh. I help you guys as much as I freaking can. I want you guys to learn. It's my goal, my passion, it's my love that you guys learn. Don't panic if you're not doing well in the Stereochem worksheet. You guys have to print it out, give your answers in pen, scan them back in, and then resubmit them. I got an email from Professor Poulos recently, Zach, and he said this exact same thing. We had a discussion recently talking about how tough it might be to grade it logistically with videos, and it was going to be way too convoluted. So we decided on the printout, handwritten answers, give out, etc. Don't be discouraged by the number of questions. I'm only going to ask you to complete 15 of those questions for me. And in the past, there used to be about 200 to 350, and I'm not exaggerating, that everyone had to complete every single question. So you guys have cake, literal birthday cake. I would not worry. But as always, email me with questions. And I highly recommend Dr. Shia's videos. Watch them. You will do well. Thank you and good luck, guys. You guys are doing great. I'm very proud of you all. Heck yeah.